Hello and welcome back to Calculus 1 section 2.4 Infinite Limits. Last time we were focusing on limits where the input is a finite value, output is the finite value. Now we are going to focus on limits that look like this. Limit x approaches some finite value a of f of x is going to produce positive or negative infinity as an answer. So infinite limits, it means answer is infinity, positive or negative, right? So infinite limits means answer is infinity. So that's what we are focusing on. And the other two iterations of this are immediately the left and right limit that also could be positive or negative infinity. So here is the limit x approaches finite value a minus, which is from the left, of f of x to be positive or negative infinity, or maybe I should say or comma. There we go. Limit x a plus, this is from the right, of f of x is equal to positive or negative infinity. So any one of these where the red one is the overall limit and the blue ones are called one-sided limits. The best example in the galaxy for this would be our good old friend 1 over x. So f of x is equal to 1 over x. When we draw the graph, we get to see these two blue limits at work. So let's go with the red approach over here, saying that the limits at x approaches 0 minus of 1 over x is going to be negative infinity. So as you are approaching on x-axis, as you are approaching x equals 0, from the left side you see that the y is shooting down to negative infinity. Last class we said that limits are the fancy way to compute the y value. So as x's approach whatever you want, you have to observe what y does. And in this case, y shoots down to negative infinity. On the other side, right, the Romeo side, we have the limits shoot to positive infinity. X goes to 0 plus, because that's from the right notation from last class. And we get positive infinity going up there. So as you can see, both of these limits over here are featured in the problem down there. Now the last class we learned that theorem which says if the left limit and the right limit are the same, then the overall limit is that value, and if they are different, limit does not exist. So over here we can actually take these two together and say that the overall limit of 1 over x as x goes to 0 from both sides at the same time does not exist because the left limit and the right limit did not match. But both one-sided limits were given there, right? You have negative infinity, you have positive infinity. What else would be a good example of something like this? Let's find ln function is another example. So if I have f of x equals, let's say, ln of x, and you would like to know what is the limit x approaches 0 plus of ln x. Well, ln x is a function that only has the positive values in the domain. Looks like that. And goes through 1 over here. So this is the standard graph for ln x. When you observe, right, you only have the Romeo approach over here, right, from the right, and clearly goes down to negative infinity. So the answer for, in our 2.4 section, right, infinite limits, answers are one of the infinities. So you have two one-sided limits, and the third overall limit, which will give you, let's do also f of x equals 1 over x squared, because that one is good. This is where the overall limit, right, from both sides is going to have infinity. So as x approaches 0 from both sides, you see that they both show. So if you use Juliet approach, which goes to positive infinity, and the Romeo from the other side also goes positive infinity, they agree that the overall limit should be positive infinity, and you can have the two-sided limit to be overall limit to be positive infinity. So all of these cases show the same thing. One limit that you will have to use graph for to solve would be the limit that contains a rational function that is shifted. So in general, you might run into a problem, let's say like x goes to 3, 1 over x minus 3. Now, this can't be solved algebraically because you have 0 in denominator. And because you have 0 in denominator, you have to use the graph. Now, on the exam, that was a good one, we don't have the access to the graphing calculator, so if you don't know that you are supposed to do what here?
Draw a graph.
Well, draw a graph, but what is the feature of the graph looking at the problem? The what? What kind of graph is this? What is the basic graph for this one? 1 over x, beautiful. And how is this graph different than 1 over x?
It's
Minus 3. What does the minus 3 do when it's directly attached to x?
positively.
Shifts it to the positive rest, so to the right. So to graph this one, you must know that you are looking at the 1 over x base graph that will be shifted to the right 3 units. So you will draw 1 over x. See, I have 1 over x up there, and 1 over x is centered at 0. Now, when you have x minus 3, it's going to be shifted 3 units to the right. So now you will see that Juliet from this side goes to negative infinity, and Romeo from this side is going to go to positive infinity, and then you know that the answer is limit does not exist. So these types of limits, you can't factor them any further. There's nothing algebraically you can do. This is the simplest form. When you look at these limits, you will have to draw the graph. And then consider left approach, right approach, and you would know what the answer is. So that is that approach method with what I do with the blue and the red. Guys, that's your method. Right? You learned that you need to do certain things with solving equations. You memorize, divide both sides, add both sides. So now in calculus you are learning that you are supposed to do the two-side approach. That is the way to solve the problem. Staring at the question gets you nowhere, right? You have to immediately say, okay, from the left, this is what I get. From the right, this is what I get. If they are the same, that's the limit. If they are different, does not exist. That is what you're learning in this class. So you have to know that theorem to survive. So now that we know the concept of what's happening, we are expecting infinity as an answer. One-sided limits also can give infinity as the answer, and if they don't agree, you get does not exist answer. So now that we know, we would like to use this. And one of the greatest uses of this would be for what we call A vertical asymptote. Known as VA. Right? So you have encountered the vertical asymptote in pre-calculus, with functions and when trig functions as well, and so on. And you are somewhat familiar with the vertical asymptote. And I say somewhat familiar with vertical asymptote because you don't have the definition for it, right? You know what it is. It's this vertical line that the function cannot go through, right? There's a wall there, you can't go through it. I mean, but let's say you can. So, vertical asymptote would be the vertical line that function cannot cross, but that's the street definition, right? We have a calculus definition that uses the limit. And we can define the vertical asymptote now as the vertical line where the one-sided limits or the overall limit are infinite. So that's how you know that there is a vertical asymptote. And with this idea, you can finally retire your good old rule: if denominator is equal to 0, I have a vertical asymptote. Is that something that holds all the time? No. There was a cheap way out in pre-calculus to tell you that, right? Because it works on a lot of examples that we carefully select. Right? Think about this. Y equals e to the x. Y equals ln x. We know it has a vertical asymptote. Is there a denominator that you can set to 0? No, right? So that story of denominator equals 0 creates a vertical asymptote is halfway true, right? Because here is a function with no denominator, and it still has a vertical asymptote at 0. So we actually have to have a really good idea through some solid mathematics of what the vertical asymptote is. So here we go. Definition. Vertical asymptote is a vertical line at x equals a for which vertical, see, I keep forgetting vertical asymptote of f of x. Vertical asymptote of f of x. I have to say that. Like if you watch the last 5 years of these streams, I always forget to write of f of x there. A vertical asymptote of f of x is a vertical line at x equals a for which the limit of f of x, see, that's why I had to say f of x up there. The limit of f of x as x goes to a is positive or negative infinity, or limit x goes to a minus, so any of the one-sided, plus minus infinity, or limit x goes to a plus of f of x equals plus minus infinity. So this definition here tells you that you get to choose, not choose, but whichever one of the three gives you infinity at the point A, as you approach A, whether it's left, right, or both sides, you are going to have vertical asymptote. Now, I think we're going to go and test those 4 examples and see that each one of them had a vertical asymptote at the number we were considering. We are going to go to 1 over x first. So you're looking at the 1 over x, and you see that the red approach gave you infinity. That's enough. We do have 1, 2, 3. You have the red, blue, and black, right? Red, blue, and black are all featured in this definition, right? Juliet approach from the left, blue one from the right, from Romeo, and overall black was there from both at the same time. As long as one of them or more are infinity, you have a vertical asymptote there. So as soon as you spot that red side, which was approached on the left, had infinity, you're done. Vertical asymptote is there. Let's go. Move to the next example. Over here, we only have the Romeo approach. There is no function to the left of 0. So the approach from the right gave us negative infinity. Perfect. Move along. Over here, we have both of those give us positive infinity, and you have the overall limit give us positive infinity. Pick any of the three. I don't care which one. There's a vertical asymptote at 0. And finally, over here, we did not write it, but I have the arrows at least. You have, if you just take a look at the red one, you approach from the left, you're approaching 3 from the left, and you have negative infinity immediately. It's enough. Sure, on the right side for Romeo, blue approach, right? You also approach 3, and you have positive infinity. This is the only thing you need. There is nothing else that you need other than this knowledge to claim the asymptote. If you are getting an infinity at the point as you are approaching it, you are going to have a vertical asymptote there. Now, it doesn't matter if it's a one-sided approach or the overall, which I tend to draw as black. So now, when we look at this, we can consider one of the problems that pre-calculus teachers would generally avoid, because the set denominator equal to 0 doesn't work really. And that would be the function. So find VA, I'll put VAs. So maybe there's a vertical asymptote or multiple vertical asymptotes. How about this? Find all vertical asymptotes of f of x equals x minus 3 over x squared minus 9. So this would not be a fair question in a class where you learn that you should set denominator equal to 0 to get your asymptotes, because it's stacked to make a mistake, right? X squared minus 9 equal to 0. What is that going to give us?
Positive, negative.
Positive negative 3, yes. So x squared equals 9. When you square root both sides, you get plus minus 3. So, see, it gives you two values. It gives you value of x equals 3, and it gives you value of x equals negative 3. And if you label them both as a vertical asymptote and you move on, well, no bueno. Let's prove why. So we're going to start and use our definition of the asymptote to see if both of these values, x equals 3 and x equals negative 3, give us vertical asymptote, in fact. So the first order of business is to check. Let's go with whatever. 3 is the first one, so fine. Limit goes to 3 of x minus 3 over x squared minus 9. Now you learned this last class, right, 2 days ago. What should I do? Factor, cancel, beautiful. So limit, x goes to 3, we have x minus 3 on top, x minus 3, x plus 3 on the bottom. These guys drop, and I have now limit 1 over x plus 3 as x goes to 3. What is the limit here? When you plug in 3 for x, 1 over 6. So limit is, let me write it in blood, not infinity. Okay? What is the requirement for vertical asymptote? Has to be one of the infinities. Is 1 over 6 that? No. Do we have a vertical asymptote at 3? No. This over here says no VA at x equals 3. It's not infinity, right? And calculus doesn't lie. Let's go check the other one, negative 3. Same thing. Limit x goes to negative 3. We have x minus 3 over x squared minus 9. You get to factor everything the same, so limit x goes to negative 3. X minus 3 over x minus 3, x plus 3. These guys cancel. And we end up with the limit x goes to negative 3 of 1 over x plus 3. Now this is one of those situations we just had. There's no more algebra to be done. We still have 0 in denominator, so we have to call graph to help us out here, because we can't plug in, because we get 0 in denominator, right? Can't plug in, and can't perform any additional algebra. So we're stuck. And because we're stuck, we immediately call. So now plus 3 on x will ask us to go and shift out 1 over x to the left, to the negative 3. And now, for the red approach, we have negative infinity. For the blue approach, you have positive infinity. But hold on, it was enough to have just one of them to be infinity. So, since limit x approaches negative 3 from the left of 1 over x plus 3 is equal to negative infinity, we have, yes, vertical asymptote at x equals negative 3. Cool. So now we have shown that the function we have, f of x equals x minus 3 over x squared minus 9, has one vertical asymptote at x equals minus 3. And we used calculus limits theorem, right, for definition for the vertical asymptote to prove that. Yes?
There's not true because we found positive.
You mean, are you talking about the blue one?
Yeah.
Well, it's the same value. So either one of them is fine. Because it's both of them are for minus 3. Okay. So just one from the left, one from the right. They're talking about the same value. So now, you might go and say, but hold on, what happened at 3? We were supposed to have the asymptote there, right? Well, there is still something happening there. Does anyone know what's going on with that one now? We know it's not a vertical asymptote because it gave us 1 over 6. So, what is it? Yes? A hole. Yes. It's going to be an open circle without any points along 3. So it doesn't have, the function doesn't have a value there. And what I'm doing now is I am going to graph this function in Desmos, and you guys are going to see what this function looks like, and also see that it has only one vertical asymptote, and you will also see that at 3 the y value will be at 1.6. So let's go and deal with that. So Really? Oh, well, such is life. So Wolfram alpha, Desmos is down. Talk to it. Graph x minus 3 divided by x squared minus 9. Wait a second. And it should provide you with the graph. Now, yeah, that's the problem. Come on. Ha. So, x minus 3 divided by x squared minus 9. And if I mean, you already see 0 to 5. You see there is no vertical asymptote at 3, right? There is a vertical asymptote at negative 3. That's negative 1, negative 2, negative 3 for the vertical asymptote, 4, negative 5. So we clearly see that the calculus worked out just fine. And you also see, if I zoom in over here, that this 3 over here is roughly 1/6. Well, it's exactly 1/6. So 1, 2, 3, 4, 5, 6. Okay. So the issue with Desmos is they don't put the open circle here. If you are to graph on your TI 83, 84 calculator, there will be a missing pixel on a graph if you zoom in. There will be a missing pixel. There will be empty spot, right? You know, it's a just monochrome screen on your calculator, and all of those pixels appear black. There will be no pixel above 3. That pixel will not light up black. So it's better than this, but that's okay. So we can clearly see that it only has one asymptote. Now, if I change this 3 to 4, immediately it's going to have 2 asymptotes. See, there you are. Well, immediately, 2 asymptotes, because now x minus 3 and x minus 3 do not cancel, and that immediately spawns the other asymptote. So only when they cancel and you have stuff like that, it will get this way. So you can change this to any multiples, so 5 and 25 in the bottom. So if this is 5 and this is 25, you would have, right, again, only one asymptote, and now there it is at 5, I mean negative 5. If I change this to a plus, the asymptote is going to jump on the other side, and it's still going to be only 1. So you can play with these graphs and learn, but the most important idea, the concept here is that the definition now, theorem, whatever you want to call it, for vertical asymptote is going to be you checking the limit and finding that infinity somewhere, whether it's left approach, right approach, or overlord limit. Now, what would the problem at exam possibly look like? It will give you the value of the asymptote. It will say, prove that the function blah, blah, blah has asymptote at 6. Well, the problem is designed so we can check your calculus knowledge. See, the wording said, prove that the asymptote is at 6. I am telling you asymptote is at 6, right? I just want you to show me that you also know that asymptote is at 6. Technically, what I'm asking there is for you to just do the limit as x goes to 6 of the function to find that infinity somewhere, right? Whether it's left approach, right approach, or overall. So, but obviously the question can be, what are the vertical asymptotes? Do we have any vertical asymptotes? Like, those are the questions as well. But through the time, I learned that if I just say, find vertical asymptotes, what you guys do is just set denominator equal to 0 and you move on. And we just saw that you can't do that, right? Because setting denominator equal to 0 gave us 3. And there was no asymptote at 3. So you can't do that anymore. You can treat those values that you get from denominator equal to 0, you can treat them all as candidates for asymptote. The only way that you know that they're asymptotes is if you do the limit. So you have to learn the theorem, the definition. Otherwise, it's not going to go well. So knowledge of how to do the limit, plus the knowledge that the infinite limit, if you get infinity, produces the asymptote. Yes?
So for like a question on the test, if it's like prove that the asymptote is 6, would we graph to find the function?
If you can't solve the limit the other way, you would have to graph it.
Like would we be given a function and be like prove that the...
Yeah, but think of this problem. You can just recast that problem into the question. Prove that function x minus 3 over x squared minus 9 has a vertical asymptote at 3.
Okay, yeah.
That's, not 3. At negative 3.
Yeah, that's
So what you would have to do is what you see on the screen right now. So 100% of what is on the screen is what you have to do. Because I already told you there is a vertical asymptote at negative 3. And this is what I'm looking for because I'm asking you to prove that it is, right? So there is an idea that the asymptote is there. There is a feeling that the asymptote is there. There is a, hunch that asymptote is there. I don't know. The dog barked negative 3 times. It was a sign, You found it in the ancient book. So many options, right? To come up with negative 3, only one way to prove it. You have to do this limit. So 100% of what you see right now on the screen is the answer to that question. You show that you know the definition right there, and then some of the work that we learn along the way to prove that. Right. So we used, in this case, right, we used the algebra, canceled everything, came up with this thingy over here, and got stuck. Can't factor it anymore, can't do anything with it. So we graphed it, and then from there, we got just the left limit was negative infinity, and that was good enough. And then we move on with our life. Fair? Well, that's it. Bye.